So we have a tiling problem here. We have a grid of length 1 into 6 and we will tile the grid in using tiles of only two colors, red and blue, and there is a condition. It says between any two red tiles there should be at least one blue tile. So we cannot have two red tiles together. So how many ways can we tile the grid without violating this condition? So if we try to tile this grid randomly, we will make some mistakes. For example, the first coloring is correct because there are no two adjacent red tiles, but the second coloring is wrong because we have two adjacent red tiles. So since we're talking about recursion, so what is the recurring subproblem here? So notice that we could give you the same problem for length, a grid of length 5 or 6 or 7. So in order to color a grid of length 7, you have to color a grid of length 6 or 5. So now let's systematically try to color this grid. So if we color this grid from left to right, so there are two cases. First case is if we use a red tile in the leftmost cell. So if we use the redmost tile in the leftmost red tile in the leftmost cell, so the cell on the right should be definitely blue, because if it is red then it will violate the condition. So the second tile must be blue. So now we have n minus 2 more cells to color. So if we say xn denotes the number of ways we can color such a grid of length n so that no two red tiles remain adjacent. So in this case we have already determined the leftmost two cells. So now we have n minus 1 more cells to color. So if xn minus 1, xn means the number of ways we can color a grid of length n, so we can color the grid which is of length n minus 2 using xn minus 2 ways. So in this case the number of coloring is xn minus 2. So there is also another case for if we tile the leftmost cell using a blue tile. So notice that the blue tile doesn't necessitate that the cell on the right should be of any particular color, because if it is red then it's fine, if it is blue it's still fine. So in this case we have n minus 1 more cells to color. So if the first tile is blue, then all we need to do is color the rest of the grid which is of length n minus 1. So if xn minus n means the number of ways we can color a grid of length n, then xn minus 1 is the number of ways we can color a grid of length n minus 1. So here we have only two subproblems. In the first subproblem we have xn minus 2 cells to color, and in the second subproblem we have xn minus 1 cells to color. So if we combine these two cases, solution for the main problem. So the total number of ways we can color such a grid of length n is xn minus 1 and xn minus 2. So we can calculate by our own hands the value of the smaller values. For example, if we have a cell of if we have a grid of one tile, so x1 means the number of ways you can color a grid of one length. So if a grid is of length 1, then we can color it using blue or red. So we have only two cases. And if we have a grid of length 2, then we can color the grid using red blue or blue red or blue blue, but we cannot color it using red red. So it has three ways that it can color itself. So notice that this recursion is very much similar to a known recursion which is very popular, the Fibonacci series. The Fibonacci series has the same recursion, which is fn equals to fn minus 1 plus fn minus 2, and these are the first few values of the Fibonacci number series. So notice that f2, x2 equals to f3. So from here we can say that xn equals to fn plus 1. So if we just can calculate the values of Fibonacci numbers, so from the Fibonacci series we can get the values of xn. So let's just look at the following code. We did nothing extraordinary here. We just write the recursion of the Fibonacci series in the second else clause, and then we just add the base cases. Base cases are the smallest values of n. So since this recurring function has to stop at some point, so for that we need to provide a base case. So now let's see how we can solve, how we can calculate the values of Fibonacci 5 using this recursion. So if we call this function using n equals to 5, then so let's call this function using n equals to 5. So notice that if n equals to 5, then the if case will not be true, so the n will go to the else case and it will call Fibonacci n minus 1, which is Fibonacci 4. So it has called Fibonacci 4. So when the function is called with Fibonacci 4, this goes to the else case again and calls Fibonacci 3, and Fibonacci 3 in turn calls again Fibonacci 2. And then we have, so since it has called Fibonacci 2, for the first time Fibonacci 2 has this if case coming true. So if n equals to 2 here, it will return 1, and so it has returned 1. So since Fibonacci 2 has returned 1, so the next call should be Fibonacci 1. So Fibonacci 1 is called, and even for Fibonacci 1, this if case will be true and Fibonacci 1 will return 1. So after the value of Fibonacci 2 and Fibonacci 1 has returned, we will sum this value, and f3 will return this value to f4. So since f3 has returned with value 2, and so now we'll call f2. So since f2 is a base case, so f2 will return 1, and f4 will add these values and it will create 3, and it will return this value to f5. So now we'll just see, this is how actually the values of Fibonacci numbers are calculated. So if I play the rest of the animation, notice that the same thing happens again and again, and finally f5 gets calculated.